So we'll go ahead and get started. For those actually watching the video at home, sorry. Model kits. People are now starting to realize they might need them, perhaps because the lab next week is the model kit lab, and so they're now trying to actually get compiled and put things together. We have a couple model kits that we can look at. So up at the front, we've got the Darling model kit, which is the one I recommend. It makes it a little bit bigger, easier to manipulate and see, and it minimizes the amount of work you've got to go through and do. Then you also get the gray box kit. Right? The gray box kit has these really hard plastic balls and these kind of sticks that come off of them. The gray box kit does have a couple different bond types. We want to be careful with those. When we use the model kits, I'll point out why you want to use one versus the other, but you're trying to use the shorter kits. So some of the reasons why I would prefer the Darling model is that when the Darling model shows up, it shows up in just a bunch of pieces. It's still connected. So you would get these things. I want to make a carbon that has 4 bonds. Done. Carbon with 4 bonds. The knot is my carbon. I have 4 bonds that go out to 4 different atoms, or 4 atoms. Okay? I want to change the identity of those atoms. I can put on the different colored balls, okay, which is what I did for here. Okay? If I go through and look at the gray box kit, what do I have to do? You're like, oh, well, it's already built, because I already built it. You have to put 4 stupid little sticks in it. Right? And depending on the kit that you buy, they sell varying versions of the black atom. Some of them have 4 connections, some of them have 6, some of them have 5. 6 and 5 connections don't work for us, and it's not obvious that they're inherently flawed, which means all of your structures don't work when you use the improper bond kit. So make sure you're paying attention to that. Okay? And then the reason why I don't like these ones is the sound every time you have to deal with it, which is fine at home. It's a problem during the exam. Okay? It usually pisses people off. Okay? Which kind of takes us to the next point when it comes to the exam. I think building a model during the exam is the wrong strategy. You should come into the exam with a model built. Okay? How many carbons do we have here?
1, 2, 6.
We have 6 carbons, so we have a cyclohexane. You should have the cyclohexane built. For those of you laughing, maybe because I was moving it around so you couldn't count it. Yeah, that was the point. Right? And I would connect technically 2 things. Red is officially for oxygen, but it doesn't really matter. You can make it be whatever you want it. But you could put 1 tetrahedral structure on it and a second tetrahedral structure on it. Okay? One of those tetrahedral structures should have as many different colors as you can fit on it. This one structure can now answer all questions. Right? I don't have to build a whole bunch of stuff. This sets me up very quickly where if I want to ask different questions, I can do quick manipulations and change it to a structure that would allow me to answer anything on the exam without having to put it all together. Does that make sense? Right. You'll see that more as you work through things, but that is the general recommendation. When it comes to homework, that's a little bit different because homework can ask really extended structures. We tend to not push too far beyond 6 carbons on exams because that takes a lot more mental processing. Right? We're trying to test, do you understand it, not how much can we break you. Homework is different. Homework is, can we break you? Can we prove to you that you actually are guessing and you have no clue what you're doing, so that you go do more work so that when you get to the exam, you're better. Right? So different goals or different objectives within those. Right? So those are those 2 potential model kits. There's another one. The tutoring center has 3 different kinds. They have the Darling, the gray box, and they have this other one, which I think is called HMS. Okay, so if you want to experiment with them before you buy, you can go there and test them out. Right? Next thing, before we even get into questions, right, I will continue to get questions on this. Okay? So if you happen to know who I'm referencing, don't stress about it. Right? But I will all too frequently get questions about, well, I don't know where this was. I didn't know this existed. Where is that? All of it is in Canvas with links sending you out to it. But that means you use Canvas. You should be using Canvas for all the lectures and the assignments. But every single one of our modules starts right at the top with this thing. Okay? That thing you should go to because it has some useful information in it. Okay? Which we talked about week 1, and I think week 2. We'll probably talk about it again. Okay? We get this big long block of text. I don't blame you if you're just going to zero that out. Okay? I did write it, but I also acknowledge that you probably weren't going to read it, so I didn't spend a lot of time writing it. Okay? The part that's going to get useful is kind of sitting here right in the middle. Right in the middle here, Google slide deck. All of this unit's lectures, they're all recorded and posted, so you have access to them. You're like, oh, it might be nice to have the slides. You do. They're right there. Click that link, you have the slides. Okay, every single slide for this unit. I would love to say in order, it's not perfect. It kind of depends on how I've decided to shuffle things as the semesters went. Didn't like where different videos were played. Okay? The next useful thing within it is the schedule breakdown on when you should be watching things in a Google spreadsheet, as opposed to within Canvas that doesn't give you due dates on when you should be watching a video. Okay? The next big useful thing is the practice exam. There's a practice exam. You should be looking at it. Okay? There are two versions of that practice exam. The first one is an open access document. Anybody in the world, as long as they know the link, maybe even Google it, I don't know, can stumble into that document and can make edits to it. Okay? So entirely open access. Okay? The second version is a blank version of the exam one, okay, of the practice exam. No one can edit that. Everybody has access to it. You can view it, you can download it, you can copy it, but you can't edit it. Okay? The blank kind of overarching goal here is that first one. Let's say you decide to go in and you want feedback on an exam question. You ask me for an answer, and I'm going to say, did you write an explanation? Explain it to me. You're like, well, no, I didn't explain it. I go, okay, I can't give you an answer. So don't ask for a key. You can. The answer is no. I'm not giving you a key. Okay? But what I will do is once you've put an explanation in there, I will periodically go in and check and be like, read your explanation and be like, that's a solid explanation. I think you know what you're talking about. Okay? Or you just said D. That's not an explanation. That doesn't explain anything. I'm not going to confirm nor deny that that was a valid answer choice. Okay? But you could provide an excuse. D is the answer because A, B, and C are all earlier in the alphabet, and clearly we only select answers at the end of the alphabet. The response you'll get will now be, that's a horrible logic system. That does not work. Perhaps you should consider this aspect of the question to help guide you to the answer. Okay? So it provides a feedback loop to help ensure that you're not blindly guessing and getting the answer right, which, believe it or not, you can do in smart work. It's hard, but some of the questions, you'll be able to just guess and get the answer right. Does that mean you knew what you were doing? No. So it can create a false sense of security going into the exam. This is my way of saying, hey, look, you don't have any security. You don't know what you're doing. You better figure it out before the exam rolls around. Okay? So it provides that kind of direct feedback that you want with the paper homework. Okay? But I can't grade everybody's. But grading one group document, yeah, I can pull that one off. Okay? The point is a learning process, though, with that document, which means that needs to be done before the exam. The exam is on Thursday, which it is, not next Thursday, but the one after. Okay? When should this exam, the practice exam, be done? Before that, when before that? Tuesday before the exam. Okay, if it's done that Tuesday. Okay? Now I get in to look at it. Let's just say I'm lucky and I get to look at it Tuesday night. Okay? And I provide feedback through it. You now have feedback Wednesday morning that you know nothing about the material. Are you going to be able to learn any of the content in 24 hours? Nope, you're SOL. When should the practice exam be done? The week before the exam. Okay? Give me a little bit of lead time to actually provide some feedback behind it, and you some time to look at it and be like, dang, I really don't know what's going on. I have to spend a week studying. That's the point. Let me make sure I know the content so when the exam hits, it's not hitting with you knowing nothing. It's hitting with you having spent some time learning the content so you know what you're doing. Kind of, sort of? Okay. I'll also push because I guarantee someone's going to go, why don't you give me a key? I need to know the answer to be able to answer it, to figure it out. The only thing an answer tells you is it allows you to reverse engineer what the answer is. That doesn't give you the information on what path you should not have taken going the other direction. Okay? What do I mean? You're asked a question, you need to know how to get to the answer. If all you've done is reverse engineer that process, you don't know how to go the other direction. You don't know how to go from a question to an answer. And you're assuming that that path is the exact same. That's great for a calculation. How many calculations do we do in this class?
0.
Pretty damn close to 0. Okay? Reverse engineering it isn't going to work. That reverse engineer will allow you to answer that question again, which is cool. You can answer one question. That's good. Except in OChem, I can infinitely vary the structures. And a very simple structure, just by adding 3 carbons, boom, it's all of a sudden a new question. It goes, oh, I've never seen this before. You've just got lost in all the other details. You have to understand the process of moving forward through the question. So an answer in and of itself is not useful. Be very careful in any scenario where all you're given is an answer and you're now backtracking, being like, oh, well, now I know it. Of course you know it. That's why it's an answer. Okay? Make sense? Cool. We'll back out of that. Which then spins us potentially to our weekly slides where I just put down random notes of things that I'm noticing from students. Or we can spin it fully back to you and say, what questions do you have? Oh, yes?
All right, let's go over question 4 and chapter 2.
Probably. I have no idea what that question is, though, so give me a second here. Chapter 2. Just for the record, in case anybody panics saying, oh, you're showing grades. These are not grades. Smart work gets massively curved, so you're not actually seeing grades here. Question 4, you said, right? Only one attempt. Oh, this one. One, two, three, four, 5. 1, 2, 3, 4, 5. Come on. First methodology is to go ahead and use a model kit, right, which is going to get a little bit challenging within this one, I think. Maybe we'll see. Right? So we're going to use our imagination in a few scenarios. Right? I have oxygen and oxygen. Oxygen is defined as red, right? Typically in our model kits. You can define it with whatever you want, but red is typically what it is defined as. Right? One of the problems with our model kits is they are designed to help us see 3 dimensions, which means we need structures that involve wedges and dashes. We do have wedges and dashes in here because those carbons are what?
2D.
I have wedges and dashes here
Yeah.
because those carbons are what?
Bonds, same plane.
It has nothing to do with them being bonded.
Towards and away from us.
Why do I need, or why should I show, or why can I show wedges and dashes off of those carbons? Said a different way, why am I not showing wedges and dashes off of that carbon? Okay, the double bond forces it to stay in the same plane, which is a decent answer behind that. Okay, so what you're referencing is that carbon is trigonal planar, and since it's planar, I can put them all in the same plane. Whereas these carbons are not trigonal planar, they are tetrahedral. Okay, how did you say trigonal planar? Why did you say it was trigonal planar?
So that center carbon, the one that's like the purple dot, has 3 different atoms around it, so trigonal planar.
Trigonal planar. You said the red ones were tetrahedral. Aren't there only 3 atoms? To be tetrahedral, it has to have 4. I only see 3.
Isn't the one that's going behind counted?
What one's going behind?
Is that hydrogen?
You mean there's an implied hydrogen? Yes, there's an implied hydrogen to satisfy the octet of that carbon. That carbon has 4 groups of electrons. Because it has 4 groups of electrons, it's tetrahedral. Because it is now tetrahedral, that requires us to use 3 dimensions. That's why we see wedges and dashes at that point. Harder question, this top carbon is what geometry? Call it the green carbons. In fact, both of those. What geometry are those? Those are also tetrahedral. Because they're also tetrahedral, shouldn't we also be using wedges and dashes? Yeah, we should, but we're not. That's a hard question. Why not? That's the beginning of lecture next week. Right? So we don't need to stress about that yet. But these red carbons have something very unique about them that makes them stand out. So what we're using in that language is now stuff that says tetrahedral, just trust me. Okay? You're using language to describe those centers and the need for wedges and dashes or not based off of general chemistry knowledge. You accept that?
Mm-hmm.
Cool. Is this a general chemistry class?
No.
Yeah.
Fix it. I don't like that language. Why should I be showing wedges and dashes? What's the property of the red atoms versus the purple atom?
The purple has a pi bond. Is that kind of what you're looking for? Oh, it has 3 groups of electrons?
Fudge me, we already said 3 groups of electrons. Pi bond is making it better. That's not the word I wanted, though.
Some
P orbital.
an
SP,
ene?
SP.
It's referencing the hybridization of that carbon. The p orbital is part of that, but I want you to pull in hybridization because hybridization is that important aspect that allows us to nail it down. When we're looking at a trigonal planar structure, our hybridization is not sp,
SP2?
sp2. 3 groups of electrons. What's the number next to the s? That's a real hard question. We'll take a guess. Is it 0?
No.
Because if it was 0, would I write s? No. Is it 2?
Yes. No.
Do you see a number 2 next to the s?
It's a 1.
It's a 1. What's 1 plus 2?
3.
3. Why did I say 2?
There's 2
The p has 2. How many groups of electrons around that carbon? 3. sp2. Ta-da! There it is. 3 groups of electrons. What's the hybridization around our red carbon? sp3. Okay. Knowing those hybridizations is an important aspect. We are responsible for shape still, but hybridization becomes a slightly more important and relevant question as we move further through the semester, including on the final. Okay. So it's okay to reference your shapes, but let's push this into those hybridizations. Okay. Oh, I have to study your model kit some more. Decided that we should actually specify that sp2. This becomes one of the problems with our model kits because our model kits are not really intended to deal with planar systems. Why do we not use them to deal with planar systems? Can you draw a planar system?
Yes.
There's no need to deal with the 3-dimensionality if you have a planar system. Right? It's irrelevant. Right? So the model kit is not intended to help with that system. It will help with this question because what we're using is the model kit to cheat our way through the assignment, which is fully acceptable. You take advantage of it. Right? So now what I want to do is build this starting structure. Right? So what is this thing with two plastic lines? Double bond, awesome. So we agree that that's the double bond. It's gray, not red. I don't care. It still represents what it does, right? Cool. Okay, I've got a carbon, followed by a carbon with the double bond, followed to a next carbon, and at that carbon, what should I see? 2 hydrogens on that carbon? I should see a dash to another carbon. Do I have another carbon? Ooh, I'm really shuffling pieces. I apologize. Alright, so I don't have another carbon yet, so I'm going to put it on there. Where do I want to put it on? Do I want to connect that carbon here or here?
In the back,
In the back. Why in the back?
because it's pointing to back on the.
The dash means it's going away, so that's where I want it to be. Okay, if I follow my structure out, continuing, I go up. Okay, and then I see a methyl straight up, right?
Yep.
Do I see that here?
Yes.
Do I see a methyl going straight up? Is there a carbon right there, right above it? No. Do I have a methyl? Ooh, I do. Do I have the methyl straight up now? Yeah, there it is. Ta-da, backbone. Is this the structure?
Yes.
Do you want to live and die by Adolfo's opinions?
Yes.
No, okay.
Tell me this part.
Why do you want to disagree with him? But don't say because it's Adolfo, that's rude. The OH is supposed to be coming out of the plane. It's supposed to be wedged. What have we now built? That structure. There it is. In all its glory. Why is that useful? Well, now I can go to A. I take a look at A. Does A perfectly overlap this? No. What needs to happen? Where's my double bond in A? It's below. I don't want to change any of these bonds. I can rotate, I can spin, I can flip. I can flip. Is the double bond going down? Yes. Lovely, look at that. Okay, do I have the carbon going up to the right? And that carbon. Do I have the next carbon up and to the left? Yeah, at that carbon, I should have a methyl coming out at me. Is that what I have? Yeah, I move to the next carbon, what do I have? I have a carbon, yeah, that looks good. And the methyl going down, where's the OH? Going away, what did I just find? Oh, there it is. But the OH is dashed and that one's wedged. I don't give a flying F, I moved the molecule. Right? You're looking at an individual frozen moment. And remember, there's no left, right, up, or down. You're changing your viewpoint all the way around the molecule, which means your interpretation of your drawing is going to change. You have to be able to interpret all of those possible drawings to decide are they the same or different. Yeah, damn. That sucks. Right? What you will find is that you get used to those manipulations and you can start to pin things down relatively quickly without using a model kit. Right? Can you? How many of you knew A was a correct answer? After we built the model kit, I was asking before we built the model kit, okay? And that becomes the struggle. You have to get used to those manipulations. That's the point of the model kit, is to set you up with those manipulations. So does that mean we just select A and we're done? No, because we also have this unfortunate statement in front. Choose one or more, okay? Which is really a fancy way of saying we drew all these structures so that you check every single one of them. Because we want you to look through at those relationships and see what's happening. Okay? That's messed up. The whole point is you should be able to see everything around the molecule. Could you see everything around that individual drawing? Were you able to interpret that A was valid without the model kit? No. So this question isn't messed up. This is pointing out that you suck at that. Right? If you're like, dude, that's brutal, I suck at it too. Okay? We all suck at it. It takes practice to build up that skill so that you can see it. And it takes time to manipulate it. This is just setting it up in a simple fashion. Next week, you're going to get hit with a sledgehammer. Right? Because what's going to happen next week? Well, let's take a look at C. Is C the same thing? No. So C we should not bubble in. But what happens next week? What is the relationship between structure C and that starting structure? Can I call them different?
So like, are you talking about like the structural thing, whatever it is? Like the difference in
So there's someone who's potentially watched into the videos. Structural isomers, stereoisomers. Okay. Are they straight up different? So we talked earlier in the semester about spontaneous, right? If I said someone was spontaneously combusting, what do we visualize? Someone just bursting into flame. Except I told you, when we look at it that as chemists, who is spontaneously combusting? Every single one of us. Because spontaneous just means it happens on its own. What is the product of combustion?
CO2.
CO2, water. What do you exhale? CO2 and water. Because why? You're combusting. That's actually why you live. Your combustion process is generating energy that you can use to cause your muscles to move. Okay? That's combustion. Wicked. Right? And it's spontaneous because it's going to happen on its own. Because when we die and we get put in the ground, you don't just see the same body. Like, you wouldn't imagine that. Digging up a grave and be like, oh my God, it's Mike still, 100 years later. That would be freaking weird. Right? What we see is a pile of bones rotting away and all that nastiness. That's because it will spontaneously happen on its own. Right? So the next unit is now going to make it difficult and say, what are those relationships between every single one of these? At this point, you're just trying to say which ones I know are identical. Does the model kit help with that?
Yes.
Yes. Okay? Are you always going to have the model kit?
Yes.
The class is designed so that you always have the model kit as far as the class is concerned. Okay? Are any of you going to become organic chemists? No. So do you need a model kit outside of this class? No. So as far as you're concerned, you always have a model kit. Okay? So you could always use the model kit. Okay? Problem with using the model kit?
Cheap way out.
People watching the video at home are like, I know why there's a problem with the model kit. Fast forward. Should be Christmas. Get to the point. Oh, they actually didn't even see the model kit. Sucks for them. Time. Time is always a factor in this. So we want to pick up the fluidity with the model kit so that we don't need the model kit and we can manipulate the structures in and of themselves. So how could we do that? Painful way to do it is drawing. So let's go through and work through that. We said A was the same. We said C was different. We used the model kits for those. So let's take a look at E. How do I get my starting structure to look like E? Okay, so what I want to do is process through what I would do with the model kit. First thing that I would do is I would flip it. Along this axis, I want to flip that because I've got the carbonyl aimed up. You call it carbonyls yet? No, the double bond oxygen straight up, and here I want it down. Right? So I'm going to flip that structure. My focal point being on that oxygen. What happens is I zigzag my way through. Whoops. Whoa. 1, 2, 3, 4, 5. 2, 3, 4. At 4, this 5 carbon was aimed straight up. But what did I do? I flipped the molecule, which means straight down. Okay? As we move through, 3. Okay, 3. That means I'm going to have that methyl somewhere up here. This was dashed going back that way. But if I flip the molecule, don't give me solid, wedged. Right? What happened to the OH? It was aimed at me, and then I'm not, okay? That's now dashed going the other way. Glad there's no cameras. Okay? So now we've got that. Is this the same thing as this? Ooh. You're already screaming no. Why are you screaming no?
The wedge and dash are going different ways.
The wedge and dash are going different ways. I don't know. The methyl is wedged, the OH is dashed. I don't quite accept your answer.
The OH moved.
Where is the OH located at?
Middle.
It was supposed to be at carbon 4. If we go through and count this out, 1, 2, whoops, the OH is at carbon 3. I've changed the atom connectivity. Can it possibly be the same thing? This is where, if you had the model kit, you could try and spin, flip, and rotate any of those bonds, and guess what you're going to find? The OH will never be at position 3. That's why we have nomenclature to tell us it's at position 4. It's never going to make that switch. There's nothing you can do about it, which means those two structures are not the same. Kind of, sort of? What we're trying to do is make those adjustments. Okay? For me, I saw the carbonyl was my focal point, so I tried to align the carbonyl to make it easier for me to interpret. Other people might have picked the OH and been the OH is at position 4, the OH is at position 3. They aren't the same. Did they get through it faster? Yeah? Okay. Have you ever sat in a math class where you're trying to figure something out and you can't figure it out and someone goes, oh, it's just this equality. You put that in and it's all done? That's the feeling, what you should feel for OChem. I didn't know that was an equality I could use. Okay? This is the problem with reverse engineering, is when you reverse engineer, you go, oh, that was the equality I could use. How did you know to use that? Okay? That's the forward process that you have to get used to. And you have to find a methodology that allows you to function through it. Even if that methodology, for me, I'm going to flip it so the backbone looked the same, takes more time, I'm at least ensuring I'm not missing other pieces. Okay? You could run the count method. Right? That won't always work, because then now you'll have to do the flip of the molecule. That's what we would have had to do with A. So you've got to figure out what method works for you, follow that method through. Kind of, sort of?
Perfect.
I don't know that I actually want to get all the way to an answer with that one, but you understand how to finish that one?
Yeah.
Does it suck?
Kind
I don't think it's that bad. I mean, you just have to do a bunch of those manipulations to see what's going on within it. But that's the process you're working through. You need that practice, yeah.
So like, if you're to turn that like 180 degrees, then does the
That. I'm going to pause right away. That. I see 6 different things up there. What that are you talking about?
the red one, the one.
Okay, this one. Turn it 180 degrees. On this axis, I get that. On this axis, I get a different thing.
The y-axis.
On this axis, I get a okay. So it's not just are we turning, what axis are you turning on to ensure that? Okay. So you want to turn about that axis 180 degrees. Okay, yeah, continue your statement. I'm going to try and draw.
So does if you turn it like that, does the HO just, does it get shown as OH or?
Ooh, good question. Let me, yeah. 1, 2, 3, 4. Do we care about the methyl with his question? No, he's only caring about what's going on with the OH, so I'm not going to worry about the methyl. I'm going to look at position 4. So 1, 2, 3, 4. Everybody see that as we did that rotation, the carbonyl should now still be down, but it's on the left side of the molecule. Everybody get that? Okay, 1, 2, 3, 4. I'm talking about 4 position. Okay, because my 1 is still starting out this direction. Okay, 4 position, I need to draw the OH. Should it be wedged or dashed? Should be wedged. Why? Okay, oops, it was going away, and we did the rotation about that axis. Now it's coming towards you. It should be wedged. Okay, and what I believe your question is asking is here, this says HO, reading left to right. Should I be writing left to right, HO over here? Okay, there's a couple people saying no, and there's a couple people like, I don't even understand why that matters.
Yes.
Yes. Okay, what do our lines show?
Wedge bond.
get rid of the wedge, because all lines, wedges are lines, show bonds. What's a bond? The sharing of electrons between two atoms. One of those atoms in this case is carbon. Is Ho an atom? Okay, I think technically it is polonium, isn't it? As I search for it, H-O, isn't it up there? That would have been nice.
Oh, yeah, it is.
Thank you, I can't see it, but it's up there. Someone confirmed it. Okay?
Oh, it is.
Are we talking about polonium?
No.
No, what are we talking about? We're not talking about, I don't know what OH is. What element are we talking about?
Oxygen.
Oxygen and hydrogen. What atom is bonded to the carbon?
Oxygen.
The oxygen, which means when I draw this out, I'm trying to show as accurately as possible the three-dimensional reality of the molecule. The three-dimensional reality of the molecule is that the carbon is connected to oxygen. By writing HO, it makes it look like connected to the hydrogen, which would then exceed the octet on the hydrogen, and that's problematic. Do people care? Yes. Will I point it out? Yes. Will I take off points? No. In this case, we would write it as OH, because what I'm trying to show is the connectivity between those. Does that make sense?
Yeah.
Real good, subtle change within our molecules. Okay? And I would recommend that you do that too, because that implies information. And by writing it HO, you change your way to interpret the information. That could lead you to a wrong answer. So you should make sure that you're showing that bond connectivity as best as possible. Have we beaten that question enough? You satisfied?
Yeah, but it's just like, when you turn it like just 180, like that, the red one, then what is it past HD? Like what is it? Like, how is it?
Okay. Okay, because now what you're saying is you did this. What axis are you rotating about?
Yeah. Or,
This one was Y. This is X. If you're doing this, you're not rotating about the X or Y, because the X is this. The Y is, fudge, don't drop stuff, this way. That's a Z axis. You picked the axis that's like the most ridiculous to try and have to draw. Thank you. Okay, Z. So what happens if we do that? Okay, you're going to rotate that back over. Okay, the oxygen that was down in this quadrant, oh fudge, I have to use my left hand. Okay, if we're here, we're rotating about that Z axis. It should now be up on the left-hand side. Pick here. Right? As we manipulate around, we can maintain those orientations. What happens with the wedges and dashes?
oh, it's, yeah, it's broken out.
Okay, so I love this question for one of the kind of natural repercussions that comes out of this. Every time we rotated again around an axis, what happened to the wedge and the dash? They changed. Careful with moved, okay? They went from wedge to dash, or dash to wedge. There it is, right? There's my thumb. Rotate about the z-axis. Is it dashed? No, it stays wedged. That particular axis, in this particular view, when we did the rotation, did not alter your wedge dashes. Right? And you're like, that's really hard to see. I can't see that, Mike. Okay. Give me a second. See, there it is. Yeah. Z-axis is this one. I still aimed at you. Okay? Make sense?
Yeah.
Okay? So this is hugely spatially oriented, and you have to be real careful with each of your permutations. And you should make manipulations off of all three axes, axi, that word, X, Y, and Z, to ensure you know what's happening with either your wedges or your dashes. Okay? And be very careful saying, oh, well, whenever I rotate around the Z-axis, it's not going to switch them. It depends on the viewpoint of the molecule. Okay? So you have to be really careful that it's dictated based off of that particular view on what's going to change or what's not going to change. So don't try and lock it in with saying, oh, it's always going to change or it won't change with this. Make sense?
Yeah.
So you want me to draw that one? I think I can pull it off. And that's what you got. So with D, that's not D.
I meant to.
Okay. Does that make, oh, is it F? Yeah, it's F. Okay.
Yeah.
Make sense?
Yeah.
Kind of getting it? You're seeing it needs some practice. Yeah, okay, good. That's what it's supposed to see. Do we have another question?
Do you have anything on like, I don't know, I think one I'm sure personally is hybridization.
What about hybridization? Just identifying it?
Yeah, I don't know, I can see the question, I'm still, I mean, I've only done the first chapter of homework. There are some videos, so I haven't gone through those questions yet. And I don't know, maybe it's just because, no offense, but there's so much like video talking that I'm like, I'm zoned out, I'm like, I don't understand what he's saying anymore.
Okay. And for the record, that's common, so I appreciate it. So let's touch on that real quickly. How much video are you supposed to watch in a week?
All of it?
Less than an hour and 50 minutes. You're like, why does that matter? That's 2 lectures. So if you're like, I'm zoning out and I don't understand what's going on in the videos, it wasn't going to be any better if we just lectured. So the point of the videos is if you're zoning out, I fully acknowledge you absolutely will. You need to stop. Not stop zoning out. Stop the video. Pause it. Do something else. Do some jumping jacks. Drink some water. Take a shower. Come back and try again. Okay? In class, you're zoning out of what I'm saying, right? You're so full of... Okay? Yeah, you're going to zone out. You're going to miss stuff. In class, there's nothing you can do to stop. You can... Mike, pause. Good luck. Okay? So it's okay to zone out. And yes, there's tons of content coming through. That's where you have to pause. You have to spend the time to go back, try and work through the questions, and do that back and forth. And yes, it's going to be painful. Don't worry about it. We can talk through hybridization. So if we're going to look at an example for hybridization, and I'm doing a variety of semi-obnoxious things within this. And actually, I like this one too. Let's do this. I drew that C really weird. Let's be extra obnoxious. Let's do that. So what are you supposed to do with hybridization? What is hybridization?
Isn't it just like identifying what's between the atoms or something? Like knowing...
Ooh, so there's a subtle question or a subtle change to the question. What you're asking about is what's between the atoms. Between the atoms is the bond. What makes up the bond? The hybridization of the atoms that made them. Okay, so if your question is about the bond and what hybridization is going into the bond, that's different than the hybridization of the atom. It's the next step. Okay, so before you do that next step, can you identify the hybridization of the atoms? Yeah? I want the hybridization for the red, the green, purple, blue, I'm out of colors. Orange. 1, 2, 3, 1, 2, 3, 4. There's 5 things there. You've had time to process while I've been talking through this. That's 5 things. Tell me the hybridization. Go.
Isn't red SP3?
There's 1. So it took you 10 seconds to get SP3 for red. Okay. That's slow. We need to work on it. That's okay. Okay, so now we're like, oh, you were timing me with your hand. Okay, so red is SP3. I heard you volunteer something else. What'd you give me, Jazz?
Still the green.
Green? What do you think green is? SP, not SP3. We still got purple, orange, and blue. Purple is also sp. Which color did you say? You said orange? Blue is not sp2. What'd you say? No. You're like, how many of them are there? It is sp3.
Wait, can you explain that one?
Oh, okay, well, yeah, you're just testing. Okay, so this is where we're walking through. Okay, you were okay with red being sp3? Yes. Why? I see one.
Blood hydrogens.
Okay, so there's implied hydrogens. So you mean we can imply things? We're allowed to imply things? To satisfy what? You want to take a look at blue for me again?
Electrons.
Yeah.
There's an implied pair of electrons to satisfy the octet, which now means there are 4 groups of electrons, which means it is sp3. Yeah? How are we feeling? You asked the hybridization question. Are you okay with these?
Yeah, the first one, yes. The third, or the blue one is just because of the lone electrons. That's the reason why we have sp3.
Yep, we have to acknowledge when we're looking at hybridization, it's electron groups. Okay? So the electron group statement goes all the way back to our Lewis structure. And when we draw a Lewis structure, we draw a box around our center atom. We don't have center atoms anymore, but we have questions that we're asking about an atom. That is by definition the center atom. Okay? So when I ask this red one, I can draw a box around it. Which of those faces have electrons? Well, 4 of the faces of that atom have electrons, and therefore it's sp3. If we move to the green one, I did see your hand. Give me a second. How many faces of that square have electrons? Which means
Just sp.
just sp. Kinda sorta?
Yeah.
So it's very located based off of just electrons. Okay, this isn't counting octets. It's just that there are electrons on that face. I don't care how many electrons. I just care that there are electrons. Okay? I find the sp3 on the nitrogen interesting because you all said sp on the oxygen, but that might have been because I typoed it initially and gave you more information. How many groups of electrons do you see around the oxygen? 1. Why are you calling it sp? Not the charge. There's an implied lone pair that maybe because I accidentally drew it, it triggered your brain and you kept it there even though I erased it. So there are still 2 groups of electrons around that oxygen, which is why it's sp.
Okay.
You happy with that level of the sp question
Yeah.
or hybridization question?
Yeah.
Okay. I'm going to ask one more and then I'm going to come back to you. Hopefully you haven't forgotten your question. Apologies. What is the hybridization of the hydrogen?
Yes.
It only has 1 group of electrons and it only has 1 orbital. It's s. It doesn't hybridize. There's absolutely no need to do any hybridization with the hydrogen. It stays s. Okay.
One thing I've been struggling with hybridization is I know we can use it to find, like, you know, if something is on the same plane with the trigonal, planar, whatever.
Mm-hmm.
You were talking about an example earlier this week. I can't remember. We talking about the used p orbitals and the unused ones. How would we? I'm just confused with how would we apply it further.
It'll pop up here. Let's not make it difficult yet, but yes, we'll do that. I now want to explain the electrons in that bond are now coming from the 2 atomic orbitals overlapping. What orbitals are being used to make that red bond?
Yes.
The hydrogens, 1s orbital, and the carbon. What's the carbon?
3p.
What's the carbon? sp3. To make that one bond, I'm using hydrogens, s orbital, and I'm using carbons, sp3. What's the dash in between? The bond connecting those two orbitals. That's what that means. All we're trying to do is add some layer of information behind what characteristics went into that. Right? Yeah, I'll find a different bond here in a second. Okay. To your question, first off, if any chemist watches this, they're going to be screaming at me for that bond, so I'm going to fix that real quickly. Why would they be screaming at me?
Which one?
The one I just erased and then drew back on. Whoops. What was it? Was that- the geometry of that, because it was linear, it should be a straight, not bent. Okay. So now this one, do I want to start with this one? We're actually not going to start with this one. We're going to shift to a different one. We said the oxygen was sp and the carbon was sp. I want to look at this black one. And for the record, you're going to, yeah, I want to look at that black one. What are the orbitals used to make that black bond?
sp2 and sp.
Okay. We have the carbon, that's an eraser. The carbon on the left is sp2 because there's 3 groups of electrons. And it is making a bond with the carbon on the right, which has 2 groups of electrons, which makes it sp. So that bond is an sp2, sp. Yeah?
Yeah.
Okay. We ready for the big level? We'll do it misleading first. What is the hybridization of that bond? So erase all our, let's not erase all the other arrows. I want to know what's going on up there. Very top, between the oxygen and the carbon.
sp.
Okay, sp makes how many bonds?
Two on each.
If I take one orbital and another orbital and I put them together, how many bonds have I made?
4. Or, one.
I make one bond. That's what happens. You overlap orbitals, you get one bond. Why is that a problem? The drawing very clearly shows 3 bonds. How could there possibly be 3 bonds if all I have is sp and sp? That's because I don't have just sp and sp. What else do I have?
The unused p orbital.
I have the unhybridized p orbitals on both the carbon and the oxygen. So when I say what's happening in that bond, really all I'm referring to is that first bond. The next bond is different from it, and the next bond is different from it. That triple bond isn't a triple bond, it's the combination of 1 sigma and 2 pi. The sigma is sp, sp, the pi is p and p. The orange is p and p. What's up? Okay. Every bond is made up of the overlap of orbitals. We okay with that? Okay. So if we're going to look at this, we've got our carbon and our oxygen. The carbon gives us an sp connection. The oxygen gives us an why am I changing the colors? Whatever. Too late. An sp connection. That's the overlap of 2 orbitals. That makes 1 bond. How do I get multiple bonds? I can't put more electrons into that exact same space, because if I put it into the same space, the electrons repel away from each other. I have to have more space to place the electrons. Okay? Shown slightly differently, if we look at the sp The sp is a combination of the s orbital and a p orbital, which is going to come in to address another layer of information. An s orbital has no nodes. What the hell's a node? What's that?
The space between the lobes, or what was it, nodes?
Sort of.
The space between the p orbital where there's no charge.
So a p orbital has nodes. Why do I have nodes? What is a node? Okay? And this now starts to verge into quantum chemistry. Okay? When we're talking about this, we're talking about the existence of an electron. How do electrons move?
Sporadically.
As waves. That's why we have the de Broglie wavelength, and you could calculate the wavelength for electron motion back in Gen Chem. Okay? They move as waves. And if I were to draw a wave, I've got a wave, right? And I could now dissect this wave, and I could say this part of the wave is very high, and this part of the wave is very low. Okay? And things that are high, I typically tend to say are positive, and things that are low, I typically say are negative. We mathematically went through and said, well, if I drop a coordinate axis on this, I get this. The bottom or the trough of my wave is in the negative realm of my coordinate square, right? And the high part is in the positive part. What happens is I transition from positive to negative. I hit a 0 point. Guess what that 0 point is called? A node. How do we see that manifest in our orbitals? Well, when we talk about our orbitals, our s orbitals, you typically just see them spheres and you're done. Okay? But when we go to p orbitals, we see the dumbbells. Do we just show them as dumbbells, or do we see some extra information potentially layered in with this? I can't believe you're going to make me do this. This is what you're saying? Oh, God. Okay, good. What are you saying? Because I really didn't like doing that. It's fair, I just didn't like doing it. What else do we see with the p orbital? Is that just how they're always drawn, just like that? No. How else are they drawn?
Horizontally. One side is positive and one negative.
So orientation, but that individual p orbital is always how it's drawn. You've never seen it represented differently.
So are you referring to like on different axes or?
Nope.
Axi?
Okay.
Sometimes you can draw in the middle of them.
Oh, right there in the middle, yeah. But that's it. You've never seen them, I believe, for those people that read the book, I believe sometimes you'll see it drawn like this. Well, but you never see the circle, the sphere, our s orbital with blue and green. You just see it all blue or all green, right? Why?
Because an s orbital is either all positive or all negative.
When we go through and look at the wave function for an s orbital, it's always positive or it's always negative. It does not have a node. The p orbital, on the other hand, does have a node. How do we visually see that? Two ways. Number one, it vanishes down to a point where we don't show any shape because that point is the node. How can we add emphasis to the fact that this is a node? We're referencing the sign of it as positive and negative. Okay? Using colors is a pain in the butt for me, so typically what you'll see me do is shade one versus the other. What we're trying to represent is the different phasing associated with it. Why is that important? Well, when we go through to do an sp orbital, we're taking the s orbital and the p orbital and we mash them together to see what happens. Okay? Since we're optimists and we love OChem, we're going to say the s orbital is positive. So there we go. There's our positive s orbital. Okay? The p orbital is both. Right? So it's going to be both positive, we'll do the dots in there, and it's going to be negative. We'll do dots in there. Why does that matter?
Because now the S has a node in it, sort of.
Like multiple nodes?
Okay? We just said these represented what?
Positive and negative?
the electron motion. How do electrons move? In waves. If we look at this, we've got our p orbital wave. We also have our s orbital wave.
Is this the beam?
What happens when I take a wave and I put another wave perfect alignment with it? It amplifies it. What happens if it's perfectly anti-aligned to it? It cancels out. So if I go through and look at this, I'm adding those two orbitals together. This part gets amplified, where they're both positive. So if I was to now try and draw that, what am I going to see? I should see a large part on the right-hand side of this. This is my hybrid. Big old large part. What happens on the other end? It cancels. Which means, do I see much on the other end? And you're like, well, I should see nothing. It's not nothing, because there's still some other stuff out there. And we see something along these lines. What we've now generated is an sp hybrid orbital. It's not an s orbital, because it's not perfectly symmetric. It's not a p orbital, again, because it's not perfectly symmetric. It has this tweaked shape on it. It generates a node within it. When we go through to look at the bond, what's happening is I'm taking that one, and I'm taking that one. They're overlapping in a constructive fashion to create a bond. Awesome. We also have their little hanger-on nodes at the other end. Right? For the triple bond, I need 6 electrons. I've now explained where I can put 2 electrons. Can I put 2 more in there? That's an orbital now. That's a single orbital. And I can only fit 2 electrons in an orbital. Which means if I want more electrons in between these 2 atoms, I have to find a new space to put those electrons. So where is there space between these 2 atoms that isn't immediately in between the 2 atoms? Above the atom and below the atom. What orbital looks like it has an above and a below? The p orbital. So if I go through and look at the oxygen, I have, ta-da, a p orbital, and ta-da, that's a stupid thing getting in the way, a p orbital. And you'd be like, well, they don't overlap. You're right, they don't overlap, but they're close enough to each other that what can the electron do?
Jump.
It can tunnel and it can jump all the way across, which means I've now created a new orbital. And in that new orbital, what can I do?
Put electrons.
Put electrons. 2 more electrons. Ta-da, I now have a
Indirect bond.
pi bond, indirect bond, accept that, keep going.
Oh, sp2.
I have a single bond with the sp-sp, and I have the double bond, because I now have a second bond. I've explained a double bond. Those empty, or not empty, but those p orbitals with electrons can now have electrons tunnel up and above. That's now saying I have 4 electrons between the atoms, which means I now have a double bond. I want a triple bond. Where's the next bond have to form?
Behind it.
The p orbital coming in and out of the plane at you. 90 degrees to the other p orbital, 90 degrees to our sigma bond. So if we were to look at this, we get electron density in kind of a cylinder all the way around that bonding axis. Can I get a 4th bond?
No.
Why not?
Well, because you'd be exceeding the octet at that point.
I don't care about octets.
But, pff,
There's no for that bond to move.
To make the bond, I have to have orbitals. Where else can I put an orbital? I can't. I've filled the entire space around it. The entire space is so full of electrons, I can't possibly get a 4th bond in there because the orbitals have already filled it out. I'm maxed. I can't drop another bond within it. Neat. So when you think about all the bonding patterns you've seen before, you saw sigma, you saw, or single, you saw double, you saw triple. Did you ever see 4? No, why not? That's not physically freaking possible. Why? Because of hybridization. The hybridization allows us to visualize that and explain the bonding patterns that we visualize. Okay? Do you need all of that? Okay? You could cop out and say, I just need a triple bond. Do I know the orbitals that make that? Yes. Okay? It's a P. I can just memorize that. And do I have to draw it? I can't draw it. I'm not going to make you draw it. Come on. If I struggle at it, that's going to be awful to try and grade whatever crap you're going to put on the paper. Because I know what I'm doing is crap, so that's not intended to be a dig. Make sense?
Yeah.
Okay, so this addresses what's going on with our hybridization. Okay, because as you talked more, it sounded like you were more concerned about referencing the bond, not the actual hybridization of the atom. The bond is the connection of the individually hybridized atoms. Why is that important? A sigma bond, not a big deal. It becomes important when we look at those multiple bonds, because those multiple bonds come about because of p orbital overlapping. Well, why do I care about sp2? What's the deal with the leftover p orbital? I can make a double bond. Right? I have the potential to do that. Kind of, sort of? Ten more minutes.
You could just list that early.
Could you explain how the orange is sp2 hybridized?
Sure. How do we determine hybridization?
Groups of electrons.
Groups of electrons. It's really easy to see the group if we put a square around our center atom. With that square around that center atom, how many faces of that square have electrons? There's 1, there's 2, there's 3. I get 3 groups of electrons. If I have 3 groups of electrons, what hybridization am I? sp2. I would love to say it's fancier than that. Actually, I would not love to say it's fancier than that, but that's all it is. Okay. Okay. What we started to touch on here, particularly with all these waves and what's happening with these hybrids, is starting to move into molecular orbital theory. Because molecular orbital theory, hybridization may or may not have been born the way I describe it, which is I got 4 things that need to be equivalent. I'm just going to make 4 things that are equivalent. I'm just going to say it happens because I know it happens. I don't know how it happens. I'm just going to do it. Okay? And that's where we get the names of SP, SP2, SP3, because it's referencing the pieces that went in to make that thing. Okay? Or make, ultimately, that new set of things. Okay? Officially, it's a lot more complicated than that, and we can't hybridize and mishmash the orbitals up. They stay as atomic orbitals, but it's how those atomic orbitals interact with each other that changes the different types of bonding patterns and anti-bonding patterns that come out of it. Okay?
You started, that's what I was going to ask about the anti-bonds actually.
Are we good with everything that's up there? Should we can do a couple examples with bonding and anti-bonding to get a feel for it. Okay. First and foremost, when we're talking about these, what we're talking about doing is bringing an atomic orbital near another atomic orbital. So what we're concerned about is the single individual relationship between those 2 atoms. Okay. When those 2 atoms come near each other, they will make a bond. That bond now is a deformed atomic orbital. It can't be an atomic orbital anymore because it's not an atom anymore, which is why we refer to it as MOs for molecular orbitals. Okay? So now let's pick some potential examples. Let's go through and look at bringing an s orbital near an s orbital. Okay? Initially, what do we have?
2 s orbitals.
2 s orbitals. Keep going. It's a really hard answer. I don't have a bond. There's no bond. I know that's kind of a stupid statement. It will come clear in a little. I'll attempt to make it clear in a second. We bring them now close to each other, close enough that the orbitals overlap. What happens when the orbitals overlap? They bond? Maybe. Go all the way back to 152. Atoms can collide and share and overlap the orbitals. That doesn't mean they make a bond. We have to have the energy, orientation, all that fun jazz. We pretty much ignore all that and just say ta-da, let's talk about what happens when it overlaps. Okay? We now have to bring in our understanding of quantum. These orbitals are assigned based off of phases. An s orbital is either all positive or all negative. Okay? So I'm just going to arbitrarily define one. I'm going to pick this one, and I'm going to say it is positive. Okay? Now when I look at the other one, it can be positive or negative. So I get two possible states that could come out of this. Okay? Just for giggles, we're just going to list them like that. Okay? Above and below, right? So we can see two states. Try and draw it a little bit better, maybe. I always screw this up. Okay? I want to know what those two states look like. Okay? So what's happening when they're both positive is I increase the magnitude of electron existence between the atoms. So now instead of looking at these two spheres overlapping each other, I want to take it to a more representative shape. It's probably going to look something more along the lines of, whoa, not like a line. Like that. Where we have decreased density on the outside and an increased appearance on the inside. Okay? That's when they've come into perfect phase alignment. What happens if they're not in phase alignment? We still have that overlap. Okay? They have to cancel out. So it's not a bond anymore, because we're talking about the scenario where the electrons can potentially interact. Okay? So I can't call it not a bond, because not a bond meant they weren't near each other. There was no chance of a bond. Okay? And in this case, we're saying the electron density doesn't want to be in the space between atoms. That's different than not interacting at all. Okay? What does that start to look like? Well, that's going to push the electrons away from the middle. That should look kind of familiar, right? That should look kind of like a p orbital. And what did we have in the p orbital? A node. We have a node here. Okay? Where one of those is positive and the other one is negative. In the other case, they were both positive, which is why we see that increase in the space in between.
So is this what it's mean when it's like something's on phase or off phase?
I don't. They call it on and off. I would have said in or in and out is usually what I use. But
It's
yeah,
just stuff I've seen about
Yep.
being in or out
Yep.
of phase.
that's what they're referencing. Okay? So what does this mean to us? Well, we now have this pretty picture. Do we really want to draw pretty pictures every single time? Probably not, so we want to use some words to describe it. This interaction shows the direct overlap of orbitals. Have we come up with a name for the type of orbital that's formed when we get direct overlap? Sigma. Direct overlap of orbitals was a sigma bond. So this is a sigma interaction. So I could now reference both of these orbitals as sigmas. I get two potential orbitals out of this. They're molecular orbitals. Okay, so both of these orbitals exist. So I can call it sigma 1 and sigma 2. Okay, and here's the next part that adds kind of the layer of confusion. In sigma 1, we've increased the density in between the atoms. And if we increase the electron density between the atom, that sounds an awful lot like a bond. So I could call this sigma 1, the 1's kind of arbitrary, but I could call that a sigma bonding orbital, not bond. And we'll come to why it's not bond here in a second. What's happening in the uppercase? Right? That now has to be anti-bonding, not non-bonding, because non-bonding meant they weren't interacting. This is saying they are actually interacting, and that interaction is a destructive interference. So that gets called antibonding. I don't want to write out the word antibonding every single time, so anytime I have an antibond, I use an asterisk, little star thing. Okay? And so I can reference this as sigma bonding, or sigma 1 bonding, sigma 2 antibonding. Okay? I said in this depiction, we haven't actually described a bond. All we described are the orbitals where we could potentially generate a bond. What do we need to have a bond?
Energy.
Define a bond. The sharing of electrons. At this point, I haven't said anything about the existence of an electron. I just said if there was an electron, this is where its probability of existing would be. That's it. Right? So once I have the probability understanding of what these things can look like, now I could say the question, do I have a bond or do I not have a bond? Right? So let's say that first atomic orbital brought in one electron. I could represent that with an arrow. There we go. I've got one electron. Where would that one electron go in my molecular orbitals?
In between.
It would go in between. Okay? So when we're talking about this, remember, this is atomic orbitals. This is atomic orbitals. My molecular orbitals are what's exactly in between here. This initial picture here is not an orbital. That's just saying that's what it looks like when we interact them. They just overlapped. That's it. So if we clean this up a little bit, how many orbitals do I have to choose from?
What?
How do I know I have an orbital?
Circle.
The circles. So there's only one circle drawn under the thing that says molecular orbitals? There's two. That's why we called it sigma 1 and sigma 2. There are two choices for where we could place the electron. Not one, there's two. Where do I place that electron? Should I place it in sigma 1 or sigma 2? Okay. Some people are saying sigma 1. Why should I place it in sigma 1? Lower energy. We look at hydrogen's one electron. Where's hydrogen's one electron? If we're talking about bonds, that's an issue. I have a hydrogen atom. It's just an atom. There's no molecules. There's no bonds. Hydrogen atom has one electron. Where's the one electron?
S orbital.
Do better. Hint. Is it the 6s orbital? Why is it in the 1s orbital?
Because that's the lowest energy.
Could it be in the 6s? I was like, no, there's no way. What happens when I pump 20,000 volts into it?
It's going to jump to that.
It jumps to that higher energy and it relaxes back down. As it relaxes back down, what happens? It emits light. That's our atomic line spectra. Our electron can exist at any one of those energy levels. Its steady state is the lowest energy. That's why we place it in the lowest energy. Do I have a bond yet? No, why not? What do I need to make a bond? I need 2 electrons to make a bond. At this point, I have 1 electron in a bonding orbital. That's not going to work. Okay? What happens if I put a second electron? Whoop. I'm zoomed in at the wrong space. Second electron, up there. Where's that second electron go?
Still the bottom.
Still the bottom. Okay. Do I now have a bond?
Yes.
Yeah. Did this atom bring in any electrons? No. Did it have to? No. Not at all. All I care about is what does the orbital look like, the probabilities when they interact, and how many electrons do I put into them? I don't care where the electrons come from as long as the electrons are present. This is why when we go through and do Lewis theory, this just suddenly dawned on me and we're way past time and I apologize for that. But when we talk about Lewis theory, I have you count your total electrons, right? And when you place the electrons in, what do? You place them on the most electronegative until what? You achieve the octet. Not how many valence electrons it has, because we don't care when we look at the molecule. We just care that they end in the molecule, period. So assigning electrons into a molecule based off of how many valence electrons they have is irrelevant and wrong physically. All I care about is that that orbital ends up with 2 electrons. What happens if this one brings in 2 electrons, just for giggles? Where do I now place those 2 electrons? In the antibonding orbital. Ah, what does that mean? Next week.